Okay, let's continue. So as I mentioned, now you simply have to look at the how many alkyl groups are attached to your alkene for you to determine whether the alkene, which alkene is much stable than the other. Okay, so there are 4 alkyl groups attached. It's tetrasubstituted. If there's only 3, it's trisubstituted. If there's only 2, it's disubstituted. But you have to know that for disubstituted alkene, there are only 2 R groups attached. The trans is much stable than the cis, but on the 1,1 carbon, this one is much more stable than the 1,2 substituted carbon. Okay, and then the least to be substituted, less stable is the monosubstituted alkene when there's only 1 R group, and the least is if there's only no R group. Okay, so let's go back to the problem here. Say Arniel.
Yes,
Arniel.
ma'am.
So
Yes. A, ma'am.
which one is the most stable? Okay.
The first one.
The first one, because it's monoditri or tetra-substituted. Tetra substituted, are you
Yes.
sure?
Yes, ma'am.
Are you sure?
Yes.
Yes, it's tetra substituted. So the first one is the most stable, followed by
The third one.
the third one, which is ditri or
Ditri. Di.
Di? Are you sure it's di substituted?
Yes, ma'am.
Okay, this is your double bond on this carbon. How many R groups are present on this carbon? You have 1. This is H3.
6.
R groups, group of atoms. You have 1. You can only have 4, no, because there's only 2 per carbon atom. So you have
Yes.
1 R group and another R group, another R group here. Lahi lang ang sequence. So another R group, CH, CH3, CH2, CH2. And there's another R group here. You have CH2, CH2, CH2. There's cyclic 1. Of course, there's only 3 R groups attached to this alkene, and this is a tri-substituted alkene. Okay, and the last one is, so you have 4 substituted alkene, 3 substituted tri, and then the last one, of course, is the second, which is a di or tri-substituted alkene. So di or tri-substituted?
Di.
Okay, it's a di-substituted alkene.
Di-substituted.
It's a cyclic one. So di. Okay, it's easy to know. Why? Because when we do reactions later for our alkanes, no, we'll be asked, there will be times and we'll be asked which one will be the major product of the reaction. Okay, let's go to the next slide. Okay, this one is simple. Predict which one is more stable. How many stereoisomers? It's very simple. How many fractions? Distill the mixture. Okay, we'll do distillation when we go with the lab. So the next activity for the lab will be distillation. Okay, so let's go with cycloalkenes. No, it's a cyclic alkene, so the 6. And the rings of cycloalkenes containing 5 carbons, atoms, or fewer exist only in the cis form. So 1, 2, 3, 4, 5, some cyclopentene, cyclobutene, cyclopropene, they exist only in cis form. For the introduction of trans double bond into ring in this small cyclic would, if it were possible, introduce greater strains. It's not possible to have the trans. So cyclohexene, it's cis, but there is a hypothetical trans cyclohexene, but it's too strained to exist even at room temperature. So this one becomes hypothetical. So the most stable one for cyclohexene is also the cis. When you go to cycloheptene, no, it has been observed spectroscopically, but it's a substance also with a very short lifetime. and has not been isolated. However, the ring is large enough to accommodate the geometry required by trans. So I don't have a figure for trans-cycloheptene. So for trans-cycloheptene, the geometry, the trans actually has been isolated. Here, the ring is large enough to accommodate the geometry required by the trans. So this is your cycloheptene, and you can actually have a trans-cycloheptene aside from the cis. So this is your cis, and it's also possible to have a trans. So for the rest, fewer than cycloheptene, no? Cycloheptene and cyclohexene, they are very not stable for the trans isomer. So the first cycloalkene that you could find having a stereoisomer of cis and trans starts with cycloheptene. So let's go with the synthesis. We still have time, 6 p.m. Now we will just go through for the slide ends. The reactions of alkenes. No? So the reaction of alkenes always, or we go first to the how to synthesize our alkenes. So that will be for the synthesis of alkenes, which involves the elimination reaction. So we have already discussed this elimination reaction in chapter 6, no? But we'll be again reiterating this one since this is how we prepare our alkenes. So the elimination reaction occurs with the alpha beta or the adjacent two atoms. There are two kinds of usual elimination reactions for the preparation of alkenes. The first one is the dehydrohalogenation of alkyl halides. The second one is the dehydration of alcohol. So for alkyl halides, you have your leaving group, you have your halide, of course, and your adjacent hydrogen, the beta hydrogen, which are eliminated HX with a base to form your alkene. The second one for the alcohol, the hydrohalogenation, is you have your OH, water is being eliminated, and you form, of course, an alkene here. So we'll look at the mechanism again, just reviewing the mechanism of the alkyl halide for the dehydrohalogenation of alkenes. So again, here you have a base, having a base always has an electron pair with it. Okay, so you have a base that would obstruct a proton to form your alkene, and you have an example that we have already discussed before, no? So of course, again, you've learned that elimination reaction will always be a competing reaction with the substitution reaction. So here you have your ethoxide trying to eliminate the protons here to form your alkene. You only get 79% for this kind of reaction. And for a tertiary alkyl halide, we get a greater proportion of our alkenes, 91%. So again, this is an example of dehydrohalogenation reaction. We call it dehydrohalogenation because we abstract or we eliminate the halogens and of course the hydrogen. So that's why dehydrohalogenation. And then next. For here, you always get an alpha beta elimination of the alpha carbon always containing the leaving group or the halides with it, and the beta would have the hydrogen. You already know this one. Hindi ko maka-next. Okay, so for your base that's used for dehydrohalogenation, no, we always use strong bases for elimination reactions. We have the hydroxides, you can have the alkoxides. No, so how do we prepare our hydroxides? Strong bases can be prepared. Example, using the potassium hydroxide dissolved in ethanol, no, or sodium hydroxide in ethanol. So when we prepare this one, the hydroxides usually prepare via a redox reaction. We have a metal, for example, sodium metal in water. I'm not sure if you're able to do that one in general chemistry, but this one is kind of dangerous. You get to produce your hydrogen gas, but the solution, you get your sodium hydroxide here. And for your alkoxides, you can have your sodium hydroxide in the presence of your alcohol solvent, ethanol, for instance. Then you can have your alkoxide. This is just a conjugate base of your alcohol, where you can prepare your alkoxide by, again, a redox reaction of your alcohol in the presence of a metal, you get your alkoxide. And example, you have your ethanol in the presence of a metal, you get your sodium ethoxide, or third butanol in the presence of a metal, potassium. Now, this is not the ion one, this is the metal. And you try to react this, you actually obtain your base, now your potassium third butoxide. Alternatively, you can also prepare via the sodium hydrides or base and react with our alcohol, and you actually produce your sodium hydride, you're able to eliminate the hydrogen as a gas. So similarly happens siya, but our agent is not the metal, but your sodium hydride. So these are the common way preparing the bases used for the hydrohalogenation. So this kind of bases that we actually produce and this kind of reactions are very strong bases, no, that could make elimination reaction possible. So for the mechanism of the dehydrohalogenation reaction, we've learned about the E2 and the E1 reaction mechanism, wherein the E2 is bimolecular, which is the rate determining step. Of course, there are two reagents that would affect the reactions. For the E1, there is only one reagent that would determine the reaction. It's unimolecular. And of course, it's the rate determining step. For the E2 mechanism, no, it involves a base that removes a beta hydrogen as the double bond forms and the leaving group departs on the alpha carbon atom. So again, this one, the same with the SN2, it's a concerted reaction. The same time that the base obstructs the proton is also the same time that the double bond is being formed and the leaving group leaves our substrate. So simultaneous concerted reaction to form the double bond. So again, also the rate of the reaction is dependent for the reaction of ethoxide and 2-bromoethane. The rate is dependent by these two reagents. And this is an example of an E2 reaction. For the E2 reaction, you have already mentioned that one, that before the formation of our product, we have a transition state that leads to the formation of the product. When the base obstructs the proton, there is a partial bond. There is a partial bond formation between the hydrogen, and a partial bond breaking process between carbon and hydrogen, and a partial double bond formation between carbon-carbon bond, and a partial bond breaking between carbon-bromine as the bromine leaves the substrate. When bromine leaves the substrates, of course, you know that it will take with it the two electrons or the electron pairs within this bond, and the formation of the double bond will come from the carbon-hydrogen bond, because when the hydrogen is obstructed, it has no electrons with it, only the base will share the electrons to form a bond with hydrogen, and you get this C2H5OH here. Okay, and of course, there is a particular orientation of the hydrogen atoms. And for the formation of the alkenes, no, it's possible that you can have many alkenes in one reaction. But if you have only a symmetrical reaction, for example, in this case, no, your bromine, it's possible, 2-bromoethane, it's possible that your base can obstruct the proton here, but since they are symmetrical, you only get one product of the elimination reaction. Here you also have CH3, 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 it's the same. The hydrogen here, and this carbon, and the hydrogen in this, and this, the other CH3 is just the same, it's symmetrical. so that you get only one product of the elimination reaction, one alkene product for the elimination reaction. Also, this one, there's only one beta hydrogen, hydrogen here. This carbon, of course, there are two hydrogens here, but either of the two hydrogens can only produce one kind of alkene. It's also possible that when you have your alkyl halides, no, such as, for example, this one, 2-bromo-2-methylbutane, you have 1, 2, 3, 4. Okay, so you have an alkane, a methyl group here. It's possible that your base can abstract the beta hydrogen from this adjacent alpha carbon here. So there are two types of hydrogen that can be abstracted. The one that comes from the CH2, Canisius CH2, CH3, CH3. Okay, I don't know why they're using the skeletal. No, I would appreciate it if they using all the bonds. No, but since you are already higher, expected to already not get confused with this one. So this is carbon, 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 hydrogen, carbon, carbon. So there's 1, 2, 3, 4, 5 carbons. The main carbon parent chain is 4 carbons, butane, and you have your methyl here, 2-methyl. So Canisia carbon hydrogen is only emphasized because we're emphasizing the hydrogen bond between carbon. Okay, so you have your base. It can attack this base here, this proton here, and this proton here. So if it attacks this one here, the proton here, so the bond, the carbon hydrogen bond will go here, get your product. So you have your CH3CH, and then you have your double bond, and your CH3CH3. So in the base abstract this first letter A, you'll get your product 2-methyl-2-butene. If the base abstract this another hydrogen here, so if it abstracts here, you get your double bond here, and then you have your CH3, and then you have your CH2, CH3. So this get your product here. So there are cases when elimination reaction would actually produce several types of alkenes. In this case, there are two types of alkene that's being produced in this kind of elimination reaction. But we always have to remember on the stability of the alkenes. Now, when we do the elimination reaction, the more substituted alkenes are, the greater will be its preference in the reaction. So you can see here, is it the same one? 1, 2, 3, 4. 1, 2, 3, 4. Okay, this is the same reaction, no? In this reaction, we actually get 2-methyl-2-butane, this one, letter A, and 2-methyl-1-butane. And you look at the stability of this. This 2-methyl-2-butane is 1, 2, 3 tri-substituted, and this one is di-substituted, second one. And in the course of the reaction for this, the more stable alkene actually is also produced at a larger quantity. You can see here, so 69% and 31%. So as it's almost 100% for the two. This one favors. This is a this is 3-degree alkyl halide. So this favors the elimination reaction, no SN2 reaction. This favors the elimination reaction here. So you see that for this reaction, a greater proportion will be produced or will be obtained for the more stable alkene. And so when elimination occurs to give the more stable alkene, okay, when elimination occurs to give the more stable, more highly substituted alkene, no, we call this one Zaitsev rule, the one that we already discussed earlier. The highly substituted alkene is the more stable one, and that is what we call as Zaitsev rule, no? Named after the Russian chemist Zaitsev, and it's also transliterated as Zaitsev, or Zaitsev. Anyway, it's Russian. So when it forms, no, when you have a base, it's redundant. When you have a base that abstracts a proton and the bond, since we form a bond here, since we form a bond, the base forms a bond with the proton, so the bond between carbon and hydrogen will not be useful for proton anymore. It will give its bond, its electrons to the double bond, and once the double bond is formed, the carbon at the bromine also leaves, and this is the transition state for the ether reaction. And the beta hydrogen and leaving group are anti-coplanar. Have here, they are anti-coplanar. And of course, the carbon double bond here has a developing character of the carbon-carbon bond is a developing character of carbon double bond in the transition state. Do you have a class now? If you have a class, it's okay if you leave. And I don't know why I can't continually go next to my slides. No. So anyway, so why is that the more substituted alkene is the more favored one or the more stable one? So we can go back to the reaction coordinate and in terms of the free energy of the transition state. No. So for example, in the reaction of the one mentioned, not the 1, 2, 3, 2 bromo 2 methyl butane, and you have your ethoxide as your base, noctiphile. Now it abstract the base. When it abstract the protons, let's say the first one, the one in, okay, when it abstract this proton here, this H2, the first one here, no, you form this one, H2. And when you form this one, by the disubstituted alkene, you get this very high delta G. It's very high. It's compared to the one with when it abstract the protons here, this H2, you get a tri-substituted alkene, you get the delta G, which is much lower. Okay, so here we can have that the preferential formation of one product having the a lower free activation energy would be formed much faster. This is what we call the kinetic control of the product here. You have a lower delta G when we produce this many tri-substituted alkene. That's why this one is much highly favored as with the other. And what we can also learn from this graph is that the transition state leading to 2-methyl-1-butene has a developing character of a double bond in the disubstituted alkene, and you can see that the transition state of 2-methyl-2-butene, you have 2-methyl-2-butene, this one here, kaning kaduhang curve. This transition state is more stable, and because transition state in this 2-methyl-2-butene resembles a more stable alkene, this transition state is also more stable. Because we've learned now that this 2-methyl-2-butene, a more stable alkene, this alkene, this product is a more stable one. You also see that the transition state of this also produce a very low delta G, and this one also is a more stable one. And we've learned from the Hammond-Leffler postulate that it's close when the transition state is much similar to the product. No, it favors that transition state. So the free energy of activation for this reaction is lower, and 2-methyl-2-butene is formed faster. So this explains why the 2-methyl-2-butene is the major product. And this is what we will say that the formation of this, the more stable one, kanang ikaduha, the highly substituted, because this is more favored due to its lower activation of energy for the transition state formation. No, we can say that this is the rate of formation of this has this kinetic control for the product formation. So it's more kinetically favored, forming this product, 2-methyl to butene, the highly substituted alkene. Okay, before we end, can I ask a volunteer to answer this question? Using the Zaitsev Rule, predict which should be the major product for the following reaction. This one is an elimination reaction. Can we ask anyone which one would be the more stable or the major product for the reaction? Is it A or is it B? Anyone?
B.
The more stable is letter
B.
Of course, the more stable product is letter B. It's highly substituted. Okay, so next meeting we will be discussing on the formation of the less substituted alkene. It's also possible. I think that ends. No, if for a less substituted alkene, it's also possible, no, to form a less substituted alkene carrying the dehydrogenation, just as in this case, no, instead of the one tri-substituted alkene here, this one is produced in a larger quantity. So when we have this kind of reaction, no, we say that it follows the what we call as the Hofmann rule. The reason for this behavior are related in part to the steric bulk of the base and to the fact that you have a base because you also have a bulky base here. You know, when you have a bulky base, actually, it favors the less substituted one because there will be a greater repulsion when it attacks the base here. So the third butyl alcohol, the reason for this behavior are related in part to the steric bulk of the base and to the fact that in third butyl alcohol, the base is associated with solvent molecules and thus made even larger. So the larger the third butoxide ion appears to have difficulty removing the internal 2-degree hydrogen. Where is your internal 2-degree hydrogen? This one here. When you have a bulky base, no, it's hard to remove the hydrogen here, getting 2-degree hydrogen here, kaysa aning primary hydrogen here. No, if the base would remove here like this one, you produce this. But if the base remove this primary hydrogen, you produce this one. Okay, because we are using a bulky base, we don't follow the Zaitsev rule for reasons that the bulky base would have a harder time removing the proton here, the 2-degree proton here, and therefore instead of producing the more stable, supposedly the more stable alkene, we produce instead the less stable alkene, which is di-substituted as compared to the tri-substituted one. So this is only feasible when we are using a very bulky base. And if we have a reaction that follows the less substituted alkene to yield in a greater amount, then we say that this one follows the Hofmann rule. No, so there are two things to consider. Usually it follows the Zaitsev rule, but there are exemptions to the rule. And this one is when we are using the bulky base, the elimination reaction proceeds to the less substituted one. And if that is the case, we say that the elimination follows the Hofmann rule. And we will see more of that hopefully if we can go to chapter 20. So that is an exemption. Okay, so that ends our session today. Your task is the following synthesis: which base would be used to maximize the yield for this product. Okay, this one is there's two ways for you. You can abstract the base, you can abstract the proton, you can abstract here, you can abstract this one. So if you abstract this one, you get actually this. If you abstract this proton here, you can get a more substituted alkene, no? But since you're able to abstract this one, the primary base, primary proton, you get this one. So your task is which base will you use to maximize the yield. So this one is the less substituted alkene. So of course, expect that you're using a very bulky base here, such as tert butoxide and tert butyl alcohol. Okay, I hope that's clear with you, and we will continue with 7.7 next meeting. So that ends our lesson today. It's already 6:30 almost. And I'll see you next meeting. Hopefully you can do your activity.
Ma'am, pwede mag-ask, ma'am.
Yes.
Regarding sa laboratory, ma'am, kanang sa table sa laboratory, unsay basis sa mga answer, ma'am, sa katarang video?
Yes, a video. You watch the video. And
Yes, ma'am, but ang gi-perform nila, ma'am, di ang tulyan lang nga kuan substance. Ang the other substance wala no.
Toluendra?
Yes, ma'am, tulyan ra ang gipakita nila. Ang the other substance wala no.
Sa ganito. Sa ganito inyong kuan. Boiling point
Ang
mo?
boiling point, yes, ma'am, determination.
Ang gipakita, toluendra. That's why you notice sa akong kuan, sa inyong answer sheet no, na ato'y gibutangan ako dash, which means kato sa experimental, you don't need to write that one. You can only predict from the literature. So you just check on the literature.
Okay, ma'am. So,
Okay, supposedly in the
laktawan na to na, ma'am.
laktawan to nyo naman to dash. Supposedly, actually, in the actual, no, you should do the boiling points of all the samples. Actually, you should have an unknown, no? But since what we are showing in the video is just you have just to look at how to determine the boiling point, the procedure, how to determine the boiling point using that method. So, dapat isa-isa, kada substance, you compare. So, you only have to perform that, at least you see how to determine the boiling point. Anyway, I have a question actually. Asking a question, like if you want to perform your laboratory activity, at home, then you can ask me and we can request. We just have to withdraw some materials. For example, next meeting we'll be doing melting point determination. I think it's possible for you to be determining the melting point at home. You can use a beaker, if not a beaker, a very transparent one. I think it's possible at home. Kana dili mabuak, no? Sa kaldero baka ninyo, they'll be using oil, or sa kalderim di ay, they'll be using oil. But you just need a thermometer and so on. So you can observe actually at home. If you are in the Butuan City area, you can borrow the materials, no? And then for the capillary tubes, I'm not sure if they have the capillary tubes. You can buy from the Mercury drugstore or other kanang atbang sa kuan. If you want to perform, but I don't know who any of you resides sa Butuan o Kabalo. But in case you are interested, you can tell me that you are interested and you want to perform. Alternately, you can just watch the procedure sa video. Do you have other questions?
Thank you, ma'am. Kada lang, ma'am. Thank you.
Okay, so that ends our session today, and let's see you next meeting or Tuesday. Let's see you on Tuesday. I hope that you were able to indicate your attendance, LMS. So, okay, that's all for today, and bye.